Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 3. Determine the centroidal moment of inertia of a circular area of radius r. Also determine its polar centroidal radius of gyration. So let's have the orientation for the solution. So this is a circle, and take note that by symmetry, the moment of inertia with respect to the x-axis is equal to the moment of inertia with respect to the y-axis. In fact, it is also moment of inertia with respect to any diametral line or diametral axis by symmetry. So let's have a horizontal strip first, and for our second part, for the solution of the second part, let's have an annular area which is simpler and easier to derive. But for this case, let's have a horizontal strip so that the strip is parallel to the x-axis, and our differential moment of inertia with respect to the x-axis is simply distance square times differential area, wherein the length of the strip is x, the distance of this point from the y-axis is x, the thickness is dy, and the distance of the strip from the x-axis is y also. And since this is the radius, so that's thickness dy, this is the radius, so that x is, by Pythagoras theorem or equation of a circle with center at the origin, square root of r square hypotenuse square minus y square. So that's the value of x, square root of r square minus y square. So the differential moment of inertia with respect to the x-axis due to this quarter circle alone is y square, constant distance square, times differential area, which is in this case x dy. So differential ix therefore is 4 times integral 0 to r of y square times differential area x dy. We multiply the moment of inertia to 4 because take note that we are only considering this strip, and there are 4, considering this quarter circle, and there are 4 quarter circles all in all when we compute the moment of inertia with respect to the x-axis. Replacing x by square root of r square minus y square. So 4 integral from 0 to r of y square square root of r square minus y square dy. So take note that our variable of integration is represented by the differential. So this is y, so 0 to r. Even if it is x, it's still 0 to r, the limits. And from calculus, when the integrand involves constant square minus variable square, we put the variable equal to constant sine of theta. So y, variable y is equal to constant r sine of theta. So we form a triangle as our guide so that we can evaluate the differential of y, which is r cosine theta differential theta. So in this triangle, sine theta is y over r, sine theta is y over r from the figure. So that differential of y is r cosine theta d theta, and this adjacent side is r cosine theta. It is also square root of, this adjacent side is also square root of r square minus y square, and it is equal to r cosine theta. So differential y is r cosine theta differential theta. And take note that when y is 0, from lower limit here, 0 over r is 0. So inverse sine of theta, or theta is inverse sine of 0. So the lower limit is still 0 radian. Then when y is r, the upper limit, r over r is 1. Then inverse sine of 1 is pi over 2. So we change limits to 0 to pi over 2. Replace y by r sine theta. So Ix equals 4 integral 0 to pi over 2 of r squared sine squared theta. This is r cosine theta, and dy is r cosine theta differential theta. Simplifying, Ix is 4r to the fourth. The integral from 0 to pi over 2 sine square of theta cosine square of theta differential theta. Then we apply Wallay formula because the limits are from 0 to pi over 2. Remember Wallay formula. The general formula is integral, definite integral 0 to pi over 2 of sine to the m theta cosine to the n theta d theta. So the Wallay formula is first we reduce the power m by 1, so 2 minus 1. Then we stop when the value reduces to 1 or 2. Since 2 minus 1 is already 1, so we stop at 1. Then for cosine n theta also, we reduce it by 1. So 2 minus 1 is 1, so we stop also at 1. So 1 times 1 times alpha. Alpha is equal to pi over 2 if both m and n are even. In this case, even, so pi over 2. Then all over sum of the powers m and n, then reduce by 2, so m plus n times m plus n minus 2 in that sequence. Then we stop when the value reduces to 2, 1 or 2. So we stop when it is 2. So that's the Wallay formula or Wallis formula if you're familiar with that. So I sub x is equal to 4r to the fourth, quantity 1 times pi over 2 all over 4 times 2. So 4 is 2 plus 2, then decrease by 2, so 2, so we stop at 2. So this one here is 2 minus 1, so that's why we stop at 1. This another one here is 2 minus 1, so we stop at 1, and this is the value of alpha when both m and n are even. If otherwise, this is equal to 1. So we copy 4r to the fourth. Cancelling out 4, so the moment of inertia with respect to the x-axis is pi r to the fourth over 2 times 2, 4. So that's the moment of inertia, centroidal moment of inertia of a circular area. So it happens that the x-axis is passing through the centroid of the circle as well as the y-axis. So note Ix equals Iy equals moment of inertia with respect to any diameter. So that means, so I will explain this further. That means that if we only consider a semicircle, the moment of inertia with respect to the x-axis for this upper semicircle or for this lower semicircle, it's the same. It is equal to half of this value, so pi over 8 r to the fourth. So again, for a semicircle, the moment of inertia with respect to the diameter or the x-axis is pi over 4 r to the fourth. It may also be the lower semicircle. In short, or in other words, if we only consider a quarter circle with respect to the x-axis or to the diameter, the moment of inertia is 1/4 of this. So Ix for a semicircle is pi r to the fourth over 8. Iy with respect to the moment of inertia of the upper semicircle with respect to the y-axis is the same because we have two quarter circles. So for the quarter circle alone, it is pi r4 over 16, 1/4 of this. Since there are two quarter circles with respect to the y-axis, and the y-axis is the common axis, then it is also pi r4 over 8 times 2 of pi r4 over 16. So again, for the semicircle, upper semicircle, or for the lower semicircle, let's just concentrate the upper semicircle, because even if we have lower semicircle, the moment of inertia is the same, because it is always positive for that case. So Ix is pi r4 over 8, half of this. Then for Iy, with this, considering this semicircle, it is also 2 times pi r4 over 16. So pi r4 over 8, because we have two quarter circles. So I hope you get it. So even if the orientation is different about the x-axis and about the y-axis, but the sense is the same. So Ix equals Iy for this upper semicircle, pi over 8 r to the fourth. So for a quarter circle alone, it is 1/4 of this value, so pi over 16 r to the fourth. Now let's proceed to the polar radius of gyration. So since Ix equals Iy, Jo, which is equal to Ix plus Iy, and in this case Ix equals Iy for the whole circle, so Jo is 2 times Ix, or 2 times Iy. Since Ix is pi r4 over pi r to the fourth over 4, so Jo equals pi r fourth over 2. So the area of the circle is pi r square. So Ko, the polar centroidal radius of gyration, is square root of Jo over area. So K sub O is equal to pi r4 over 2 divided by pi r square. So this is square root of r square over 2. Therefore, Ko, the polar centroidal radius of gyration, is r over square root of 2 for a circle with respect to the centroid. So that's the polar centroidal radius of gyration. Then another derivation is, let's compute the polar moment of inertia of the circle, and let's consider an annular differential annular area, so that the derivation would be simpler. So the radius of this annular area, differential annular area, is r as shown. The thickness is dr. So the differential polar moment of inertia is by principle r square differential area. So the differential JO is r square differential area. The differential annular area is, for you to imagine, you cut it, flatten it out, so it is a rectangular strip. The length of the rectangular strip is 2 pi r, the circumference and the thickness is dr. So dA is 2 pi r circumference times thickness. So JO therefore is integral of r squares from 0 to r of differential area circumference, cut it out, flatten it out, 2 pi r, the length, thickness dr. So this is 2 pi, integral of r cubed dr is 2 pi, then integral of r cubed dr is r to the fourth over 4 from 0 to r. So that this is pi r, 2 pi r to the fourth over 4, or pi r fourth over 2, which is the same as this. And by symmetry, Ix equals Iy equals, in fact, I with respect to any diameter. So you equate this to 2 times Ix or 2 times Iy, and we can derive back I with respect to x, Iy, I diameter is pi over 4 r to the fourth. So that's it, and I hope that you're now familiar with the moment of inertia of a circle, quarter circle, semicircle with respect to the x or y axis. Level 4. Determine the moment of inertia of the shaded region shown with respect to A, x-axis, B, y-axis, And we'll use this to generalize the calculation of the moment of inertia for common figures. So for the solution, so let's have a horizontal strip first, and we'll use that strip for both the derivation of the moment of inertia about the x-axis and about the y-axis. So if we have a strip here, the distance from the x-axis is y, and the distance of this left point of the strip from the y-axis is x. The right point from the y-axis is b, as shown. The distance of the strip from the x-axis is y. The thickness is differential y. Same is true if extended to the y-axis. So if extended to the y-axis, the thickness of this strip is dy. So for A, differential Ix equals constant distance square y square times differential area. Differential area is the area of this strip. The area of this strip is equal to the length of the strip times thickness of the strip. The length of the strip is b. This is b, then minus x, while the thickness is dy. So therefore, dA is b minus x times dy. So Ix therefore equals integral from 0 to h of y squared, and differential area is b minus x dy. Now the variable of integration is y because of this differential y here. So the limits would be from lower 0 to upper point h. So 0 to h, then we must express x in terms of y from this equation here. Y equals kx to the n. So at this point, y is h, x is b. So h equals k b to the n. Therefore, y equals k, which is h over n, h over b to the n, times x to the n. So y equals h over b to the n, which is k x to the n. X therefore is, if we raise everything to 1 over n, so x is b to the n over 1, b to the n quantity to the 1 over n is b, then y to the 1 over n divided by h to the 1 over n. So x is b over h to the 1 over n, x to the y to the 1 over n. So replacing x here by this value, so Ix equals integral 0 to h of y squared, quantity b, minus b over h to the n, y to the 1 over n dy. So the integral of the first term is by squared. Integral of by squared is by cubed over 3. While the integral of the second term, because we have b over h to the 1 over n, y to the 2 plus 1 over n. So by power formula, it becomes y to the 3 plus 1 over n, then divided by 3 plus 1 over n for the second term. So Ix equals by cubed over 3 minus b over 3 plus 1 over n. This is the power of, after we integrate 2 plus y over n. So again, integral of y to the quantity 2 plus 1 over n. So by power formula, it becomes y to the 2 plus 1, so 3 plus 1 over n over 3 plus 1 over n. Then we just copy the constant b over h to the 1 over n. So limit 0 to h. So this is bh cubed over 3. This is b h quantity 3 plus 1 over n over 3 plus 1 over n h to the 1 over n. Or this is h cubed times h to the 1 over n, so that we can cancel h to the 1 over n. There is h cubed here. Then simplifying the denominator, this is 3n plus 1 over n. And the denominator n is transferred to the numerator by algebra. So Ix equals bh cubed over 3 minus nbh cubed over 3n plus 1. So again, this is supposedly, after we substitute the upper limit h cubed times h to the 1 over n, so we cancel out h to the 1 over n. So there is h cubed here, which is this. Simplifying this is 3n plus 1 over n, 3n plus 1 all over n. So the denominator of the denominator n is now in the numerator by algebra. So this is the LCD, 3 times 3n plus 1. So simplifying, Ix equals 3n bh cubed plus bh cubed, then minus 3n bh cubed all over 3 quantity 3n plus 1. So we can cancel this 2, and therefore we can now derive Ix bh cubed over 3 quantity 3n plus 1. So that's the formula, and hope that you will remember this formula, or you memorize that formula, or else you derive back to the general uh, or the basic setting up of differential moment of inertia with respect to x or y. Then for moment of inertia with respect to the y-axis, so we have a rectangular strip, and we want to derive the differential or elemental moment of inertia with respect to the y-axis. So it is just a rectangular strip with respect to the base, where the base is dy and the height, there are two heights, b and x. So for this rectangular strip, it is 1/3 of dy b cubed. Remember the basic formula for moment of inertia of rectangle with respect to the base. Then minus 1/3 dy height cubed. So differential iy equals 1/3 b cubed dy minus 1/3 x cubed dy, or 1/3 base dy height cubed. Factor out 1/3 and dy, so iy equals 1/3 integral of quantities from 0 to h of b cubed minus x cubed dy. So the variable again is y, so that's why it limits 0 to h for this strip. We replace x by this value, so if we have x cubed here, this becomes b cubed y to the 3 to the n over h to the 3 to the n, as shown. So iy equals 1/3 integral from 0 to h of b cubed minus b cubed over h to the 3 over n y to the 3 over n dy. So the integral of the first is b cubed y, and the integral of the second is b cubed over h to the 3, and we just copy that. Then this is y to the 3 over n plus 1, then divided by 3 over n plus 1. So iy equals 1/3 quantity b cubed y minus b cubed over h to the 3 over n y to the 3 over n plus 1 all over 3 over n plus 1 by power formula, then from 0 to h. Factoring out b cubed, then this becomes h. So take note that h to the 3 over n will be cancelled, because when we substitute the upper limit h here, by the way, the lower limit would be 0. So when we substitute h upper limit, this term is h to the 3 over n times h. So we can cancel h to the 3 over n. So this is just h. Then the denominator 3 plus n over n, and we'll put n in the numerator back. So iy equals b cubed over 3 quantity h minus nh over 3 plus n. So factor out h, then we'll have b cubed h over 3 quantity 3 plus n minus n all over 3 plus n. So cancel n, and since here this is just 3 divided by 3, so we can cancel also 3. So iy equals b cubed h over 3 plus n. So that's the moment of inertia with respect to the y-axis. For our second solution, let's consider vertical strip. It may be simpler for vertical strip. The height of the strip is y, and the thickness is dx this time. So that differential ix is moment of inertia of rectangular strip with respect to the x-axis is 1/3 of y cubed dx. So that distance is also x. So differential Ix equals 1/3 of y cubed dx from the differential moment of inertia of a rectangular strip with respect to the x-axis. So y, the variable here is x this time. So we express y in terms of x, and this is the value of y. If we cube it, then h cubed over b to the 3n, then x to the 3n. So Ix equals 1/3 integral 0 to b this time because the variable is x, 0 to b, left value 0 to right value b, of y cubed, so h cubed over b to the 3n, x to the 3n, which is now this dx. So this is constant, we put it before the integral sign, then integral of x to the 3n dx is x to the 3n plus 1 over 3n plus 1. So Ix is h cubed over 3b to the 3n, x to the 3n plus 1 over 3n plus 1 from 0 to b. Now, when we substitute the upper limit, this is b to the 3n times b, so we can cancel b to the 3n, so the simplified value here is b. So bh cubed over 3 over 3n plus 1, which is now the same as this bh cubed over 3, 3n plus 1. So Ix is h cubed over 3 b to the 3n, then b to the 3n plus 1 over 3n plus 1 minus 0. So again, b to the 3n plus 1 is b to the 3n times b, so we can cancel b to the 3n, and it is now of this form. So it's the same. So likewise, considering the vertical strip, moment of inertia with respect to the y-axis is, in this case, the strip is parallel to the y-axis. So differential Iy is distance square x square, differential area, which is area of the strip, y dx. So differential Iy equals x square, differential area, again, the area of this strip is y height times thickness dx. So Iy therefore equals integral 0 to b of x squared, then quantity y dx. We replace y by h over b to the n x to the n. So Iy equals integral 0 to b x squared of h over b to the n x to the n, then dx. So this is constant, h over b to the n, and x to the x squared times x to the n is x to the 2 plus n. The integral of x to the 2 plus n is x to the 3 plus n over 3 plus n. So it is now clear. So Iy is h over b to the n, x to the 3 plus n over 3 plus n from 0 to b. So we have, when we substitute the upper limit, this is b cubed times b to the n. So we can cancel b to the n. What remains here is b cubed, then times h over 3 plus n. The lower limit would be 0. The value is 0 when you substitute the lower limit. So Iy is clearly same as this. So b cubed h over 3 plus n. So that's it for this problem. Level 4a. Use the results in problem level 4 to verify moments of inertia of areas for cases where a, n is 0, which is a rectangle, b, n is 1, which is a triangle, and when the degree of the curve is 2, which is a spandrel of parabola or complementary parabola. So we have the same guide, same shaded area as in level 4. So for the formulas, remember that Ix of the shaded figure is bh cubed over 3 quantity 3n plus 1, if you can remember the solution, while Iy is bh cubed over 3 plus n, can remember from level 4. So for part A, rectangle, n is 0, so it is a rectangle, so n is 0 means the degree is 0, so y equals constant. So y equals h in this case. So that's why it is a rectangle. And we expect that the moment of inertia with respect to the x-axis is bh cubed over 3, which is the moment of inertia of the rectangle with respect to the x-axis or with respect to the base. Then Iy is also bh cubed over 3, where the base is h this time because this is coincident with the y-axis, and h is b. So b cubed h over 3. So for n equals 0, Ix of rectangle is bh cubed over 3, quantity 3 times 0 plus 1. So this is 1. So bh cubed over 3, which proves that the moment of inertia of a rectangle with respect to the base is really bh cubed over 3. Iy is b cubed h over 3 plus 0, so it's the same b cubed h over 3. It just happens that b is the height of the rectangle orient when one edge is oriented to coincide with respect to the y-axis. So it is the same b cubed h over 3. So it's b that is cube in this case because the base is like the h in this case. Then for triangle, so that's the orientation. So substitute here, Ix is bh cubed over 3, quantity 3 times 1 plus 1. And I hope that you can memorize or remember the moment of inertia of a triangle with respect to the base, even if it is below the x-axis, even if it is here, even if the triangle is oriented in this manner, it is bh cubed over 12. 3 times 1 plus 1 is 4 times 3, 12, so bh cubed over 12. Then Iy, using this formula, b cubed h over 3 plus 1 is b cubed h over 4. So I hope you can familiar with that. Or the other way to derive this is moment of inertia of a rectangle, which is b cubed h over 3, minus moment of inertia of a triangle with respect to the y-axis, which is b cubed h over 12. b cubed h over 12. So you do that, b cubed h over 3 for the rectangle, then minus the triangle b cubed h over 12. b cubed h over 12. And you will get the same result, b cubed h over 4. Now, if the triangle is oriented in this manner here, like that, so the moment of inertia with respect to the x-axis is the same, b cubed bh cubed over 12, while the moment of inertia with respect to the y-axis, because this h here is coincident with the y-axis, so it is like a triangle. Moment of inertia of a triangle with respect to the base, and the base this time is h, the height is b, so it is b cubed h over 12. Iy is b cubed h over 12, same as that, because this is the moment of inertia of a triangle with respect to the base, bh cubed over 12. So with respect to the y-axis, it is also the same triangle that is oriented. The base is now h and the height is b, so b cubed h over 12, like that. Finally, for spandrel of parabola or complementary parabola, n is 2. Then Ix is equal to bh cubed over 3, quantity 3 times 2 plus 1. So this is 7 times 3, so bh cubed over 21 Ix. And for Iy, b cubed h over 3 plus 2, so it is b cubed h over 5 Iy. So that's it, and I hope that you can remember this guide so that you can verify the moment of inertia of a rectangle, triangle, and spandrel parabola with respect to the x or y axis. And that's a must because these shaded areas are common in structural engineering. In fact, this one is no longer common, but for other branches like fluid mechanics and hydraulics, this area would also be common. Level 4B, determine the moment of inertia of the shaded region shown with respect to x-axis, b, y-axis. So here is the given figure, and take note that this figure here is actually rectangle minus the figure in level 4. So the idea therefore is we compute the moment of inertia of this shaded figure as moment of inertia of a rectangle with respect to the x-axis minus the formula, general formula for moment of inertia for the area under this curve. But before that, let's have integration solution. So let's have a horizontal strip, and the length of the strip is x, the thickness is dy, it crosses y, and the differential moment of inertia, because this is y, distance of the strip from the x-axis is y, and the basic is differential ix is equal to y square differential area, where differential area is area of the strip x times dy. So differential ix equals y square differential area, and differential area is x times dy, the area of the strip. So the variable of integration here is y, so limits would be from 0 to h. So we express x in terms of y. So from this equation, y equals kx to the n, then x raise everything to 1 over n. So x therefore is y to the 1 over n over k to the 1 over n. But y, when y is h, x is b, so h equals k b to the n from this equation. Y is h, x is b. So that means k is h over b to the n. So x therefore is y to the n over k to the 1 over n, and k is, from this equation, h over b to the n. So simplifying, x is y to the n times b, because b to the n over b to the n to the 1 over n is b, and we make it in the numerator. So x is b, y to the 1 over n over h to the 1 over n. So substitute here, ix is equal to integral from 0 to h of y squared, then x b y to the 1 over n over h to the 1 over n dy. So we put this constant before the integral sign. Ix is b over h to the 1 over n, then integral of y to the 2 plus 1 over n dy. The integral of y to the 2 plus 1 over n by power formula is y to the 3 plus 1 over n over 3 plus 1 over n. So ix is b over h to the 1 over n. Then we have y to the 3 plus 1 over n over 3 plus 1 over n from 0 to h. So lower limit will just be 0. So substitute. So we have ix equals b over h to the n, h to the 1 over n. Then because the simplified form of this denominator is 3n plus 1 over n, so the denominator of this n is now in the numerator. Then substitute h cubed, h to the 3 plus 1 over n is the same as h cubed times h to the 1 over n. Then the denominator is 3n plus 1. Lower limit 0, so it's minus 0. So we can cancel h to the 1 over n. So ix therefore is nb h cubed over 3n plus 1. So that's the moment of inertia with respect to the x-axis of this shaded figure in general, if the curve here is y equals kx to the n. So that's it. Then for Iy, differential Iy, because we have a rectangular strip with respect to the base, so it is 1/3 x cubed dy. Differential Iy is 1/3 x cubed dy from our guide for a rectangular strip moment of inertia with respect to the y-axis. That's the differential moment of inertia of this elemental strip. So x cubed is, we just make this cube. So differential Iy is 1/3, then b y to the 1 over n over h to the 1 over n quantity cube dy. The variable of integration is still y. So simplifying, differential Iy is b cubed over 3h to the 1 over n, y to the 3 over n, then h over 3 to the n, dy. So integrating, Iy equals b cubed over 3h to the 3 over n, then integral from 0 to h of y to the 3 over n dy. The integral of y to the 3 over n dy is y to the 3n plus 1 over 3 over n plus 1. Y to the 3 over n plus 1 over 3 over n plus 1. So Iy is b cubed over 3 h to the 3 over n quantity y to the 3 over n plus 1 over 3 over n plus 1 from 0 to h. So again, the denominator is 3 plus n over n. So we transfer n denominator here to the numerator. And this is h to the 3 over n times h, so that we can cancel h to the 3 over n. So Iy equals n b cubed over 3 h to the 3 over n, quantity h to the 3 over n times h over 3 plus 1, 3 plus n. Simplified form of this. Then minus lower limit 0. So we can cancel h to the 3n. So Iy is n b cubed h all over 3 quantity 3 plus n. So Iy is n b cubed h over 3 times quantity 3 plus n. So that's it. And for the simpler derivation, so Ix is again Ix of a rectangle, then minus Ix of this supposedly shaded figure, which which is derived in level 4 problem. And to remember that it was bh cubed over 3 quantity 3 times n plus 1. So Ix is bh cubed over 3 for the rectangle minus bh cubed over 3 times quantity 3n plus 1. Remember this formula from level 4. So simplifying, this is the LCD. Ix equals 3n bh cubed times 3n plus 1 minus bh cubed all over 3 3n plus 1. So we can cancel bh cubed times 1 minus bh cubed. So what remains here is 3n bh cubed all over 3 3n plus 1. So we can cancel 3 further. So we have n bh cubed over 3n plus 1. This is the same as that. Likewise, Iy is Iy of rectangle. Imagine a rectangle, this rectangle here. Then we must subtract the moment of inertia with respect to the y-axis of this supposedly imaginary shaded figure from level 4. The formula was b cubed h over 3 plus n. So therefore, Iy is b cubed h over 3 minus b cubed h over 3 plus n. Iy is b cubed h over 3 for the rectangle minus b cubed h over 3 plus n for the moment of inertia of this figure, this one, with respect to the y-axis given by this formula or derived. This is the formula when we derive it from level 4 problem. So this is the LCD. So Iy equals b cubed h times 3 plus n minus 3 times b cubed h all over 3 quantity 3 plus n. So 3b cube h out. Then in the numerator, what remains is n b cube h, then divide by copy the denominator. So n b cube h over 3 plus n, which is the same as that. So that's it, and I hope that you can derive other situations using the derived formulas from level 4, and you may also use this orientation of area for other cases.